To finish off our chapter on hypothesis testing, we're going to talk about errors and power. So let's start off with errors. Once we make a decision for a hypothesis test, are we always right? No, we're not. So let's suppose that we know the null hypothesis is true. We make one of two decisions. If we reject the null hypothesis and the null hypothesis is actually true, we've committed what we call a type 1 error. If we fail to reject the null hypothesis, but the null hypothesis was actually true, we were correct. If we're under the situation where the null hypothesis is actually false, and we reject the null hypothesis, then we're correct. If we fail to reject the null hypothesis, so we kind of stayed with it, but the null hypothesis is in fact false, then we've committed another type of error called a type 2 error. So a type 1 error can happen when you reject the null hypothesis, and a type 2 error can happen when you fail to reject the null hypothesis. A type 1 error is rejecting the null when the null is actually true. The probability of committing a type 1 error is denoted by alpha. When you set the alpha level of a test, you are actually setting the type 1 error rate. Remember, we do the hypothesis test under the assumption that the null hypothesis is true. A type 2 error is failing to reject the null hypothesis when the null hypothesis is false. The probability of making a type 2 error is denoted by beta. So instead of alpha, it's beta. Beta is the probability of a type 2 error, which is the probability of failing to reject the null given that the null is false. Now, we've got those two kinds of errors that we can commit, but we also have a good decision that we make that we want to keep a high probability on. When making a decision in a hypothesis test, we can be correct. The statistical power of a hypothesis test is the probability of rejecting the null when the null is actually false. So that's a good thing, right? We want to reject the null if the null is false and find a correct alternative hypothesis. So power is the probability of rejecting the null given that the null is false. Power is the complement of beta, the type 2 error rate. So remember, beta is the probability of failing to reject the null when the null is false. Power is the probability of rejecting the null when the null is false. So they're complements of each other, and so power can be computed by taking 1 minus beta and vice versa. Beta is 1 minus power. Now to picture what power is, this picture may or may not help you. Notice that the top half of the screen is under the reality of the null hypothesis being true, which is what we assume when we're carrying out a hypothesis test. So up here, let's assume we have a less than alternative hypothesis. The alpha level is in the lower tail, okay? So if you reject the null hypothesis, you've got alpha right there. On the right side of the line, you've got the do not reject the null hypothesis. Now, that's what we're used to doing when we do a hypothesis test. Now think about the situation where the null hypothesis is actually false. Then there's a different distribution, which we haven't talked about yet, the alternative hypothesis distribution. If you reject the null hypothesis when the null is false, so to the left of the red line, you're in the situation of power. If you fail to reject the null hypothesis when the null hypothesis is false, that's the definition of beta. So you can see that power and beta are complements of each other. And you can see that power is kind of related. Power and beta are kind of related with that alpha level, but not directly. It turns out if you lower the alpha level, you actually increase the beta. Think about sliding this vertical red line over to the left, okay? But in reality, we actually set the alpha, so we're not going to worry too much about that. We do want you to think about other things that affect power, though. So if you increase alpha, you just need to know you're going to increase your power. But we don't usually want a high alpha, but that is one way to increase the power. In practice, we typically set the alpha, and then we think about increasing our sample size. Increasing the sample size will increase power. Also, if your true parameter value, the distance from it to the hypothesized parameter value, is large, then you're going to increase power. So the further away that reality is from your assumption, the better it is, the more likely it is that you'll be able to find it. And then, of course, if there's a lower variability in the population, that gives you more power, but that's not something you can control. So we set the alpha and we change the sample size is what we typically do in practice. So how does this look? We want a power to be typically greater than 80%, so how do we accomplish that? In practice, we set the alpha based on industry standard, legal precedent, whether it's worse to make a type 1 or type 2 error, etc. And then we construct a power curve with power on the vertical axis and differing values of the true parameter on the horizontal axis. And then we overlay power curves for different sample sizes. So here's an example of a set of power curves for the test of the null hypothesis that mu equals 12,000 against the alternative that mu is less than 12,000. Now, how can we tell the alpha level of this test? The alpha level is going to be the height where these lines meet down here. So we can see that the alpha level of this test is 0.05. How could I tell the direction of this test without having this information up here given to me? I know it's a less than alternative hypothesis because I'm only considering values for the parameter that are less than my null hypothesized value of 12,000. So the power curves come together and kind of begin at the null hypothesized value, which is 12,000. I can tell that the alternative is less than because I'm only considering values less than 12,000. And notice that my biggest sample size is the top curve. The n equals 100 curve is this top one. As I get a bigger sample size, I increase my power. So those are some things that I want you to be able to recognize about a power curve. Now, there's a different way to look at a power curve, and that's through something called an operating characteristic curve. And this is actually where you put the type 2 error rate on the y-axis instead of the power. And you know, a type 2 error is a complement of power, so it's just flipped upside down. So again, your null hypothesized value is going to be where these lines meet. But instead of the alpha level being printed here at 0.05, it's 1 minus the alpha level, 0.95. And of course, we can still tell that our alternative is less than because we're only considering values to the left of 12,000, less than 12,000. And again, your biggest sample size leads to your highest power, the lowest beta, which is the highest power. All right, so what do power curves look like for a not equal to alternative hypothesis? Well, your null hypothesis is where they come together still, mu equals 12,000, but this time we're considering values less than 12,000 and also greater because our power curves go each way, so that's how we know it's a not equal to alternative hypothesis. And of course, if we were in the situation where we had a greater than alternative hypothesis, it would just look like the right side of this picture, where we were only considering values greater than 12,000. So that's a brief little introduction to errors and power in hypothesis testing.